Welcoming everyone to session 2 of the event today. In this session, we are going to discuss resource mapping, volumetric, and risking. I would like to take the opportunity to introduce all the eminent speakers. We have Dr. Pierre-Yves Chenet, CTO, Beicip-Franlab. Dr. Chenet is Chief Technology Officer for Exploration and EOR at Beicip-Franlab. He is an AAPG, SPE, and EAGE member. He is a geologist, petroleum system, and reservoir expert, geophysical, geological characterization, and EOR with more than 35 years of experience. We welcome you, sir. I would also like to welcome Dr. Owen Sutchliffe, Head of Global Geology and Geophysical Practices, Halliburton. Dr. Sutcliffe is based in Halliburton's offices in Abingdon, UK. Dr. Sutcliffe joined Landmark in 2014 after the acquisition of Neftix Petroleum Consultants and subsequently managed the Neftix Insights portfolio of products. We welcome you, sir. I would also like to welcome Mr. Debjyoti Das, Technical Solutions Manager, Schlumberger. Mr. Das is a geologist by background and has been working with Schlumberger for last 10 years. He has been involved in various exploration projects in Indian sedimentary basins as a petroleum systems modeler and has had an experience of evaluating the play and prospecting risking for multiple projects. We welcome you, sir. I would also like to welcome Mr. Asit Kumar, HOD, Directorate General of Hydrocarbons. He is going to be the moderator of the session today. Mr. Kumar is currently heading the National Data Repository of Directorate General of Hydrocarbons, a regulatory body under Ministry of Petroleum and Natural Gas, Government of India, advising DGH in all matters related to geophysics. We welcome you, sir. And now may I request Mr. Asit Kumar to commence the session, please.
Okay. Thank you, Chandrima. So welcome to all to this session 2, and we have 3 interesting presentations in this session. I think Dr. Pierre is slightly late, so we can start with the second presentation. We are slightly
Dr. Chenet is here, sir. Dr. Chenet is here.
Okay, here. Okay, fine. So then we can start in the usual sequence that we have.
How can I connect?
So without losing time, and since we are slightly behind the schedule, let's start with the first presentation. And over to you, Dr. Pierre. You can start your presentation.
Thank you. Good day, everyone. I'm going to share my screen. So the purpose of my presentation today is to show the added value of process-based modeling in exploration as part of this workshop on the increased focus on play-based exploration. What I'm going to discuss today are basically 4 topics. The first is, why do we do play-based exploration? How we practice play assessment using process-based modeling. And I will show 2 applications, typically one on a nearly new frontier basin and the other one on the mature basin. Needless to say that the new frontier basin was new when we did the study and now is a mature one. We'll see what was the real added value of the model there. And finally, discuss quickly how we can build a lead prospect portfolio driven by play assessment. So, in our view, we do play-based exploration, having in mind the exploration objectives, which is to detect leads and prospect, which are characterized by their prospective resources, according to the widely accepted petroleum resource management system definition, and at the same time evaluating the geological and development risk. As we all know, leads and prospects are characterized by 4 petroleum system components: the trap, so the volume of the trap, the rock volume; the reservoir, its presence and its quality, characterized by its porous thickness and permeability; the seal, its efficiency; and last, of course, the oil and gas charge. The advantage of play-based evaluation incorporating process-based modeling is that it provides a consistent and quantified geological framework for evaluating the quality of each component and the associated risk. For instance, for a trap, we want to know what, just as an example, the probability of success that the gross rock volume would be bigger than 50 square kilometer for the area and maybe 100 meters of average closure. Same with the reservoir. What would be the probability to find a porous thickness of more than 3 meters? For a seal, what would be the probability to the seal be able to retain more than 200 meters of oil column? And lastly, for the charge, probability to get more than 5 million barrels per square kilometer charge in the drainage areas. As you can see here, I've been putting numbers, not a qualitative consideration. It's good, bad, or it's a good source rock, or it's a good reservoir. No, let's be honest. We are interested in volumes, therefore numbers. Since, as we all know in this session, I assume that 4 petroleum system elements are needed to ensure some success. We need a sufficient gross rock volume, and this comes from classical structural interpretation, mostly from seismic data. For the reservoir, we need to find a certain porous thickness, and we will be looking at geobodies and depositional environment, and their modeling can bring us something, since in many situations the sedimentation process can be simulated through diffusion equations, for instance. For the seal, we also need to have a sufficient capillary pressure because this is directly related to the ability of the seal to retain a certain column of gas and oil. We need to find its extension, homogeneity, and their modeling can help us as well by looking at the presence on one hand, and looking at the capillary pressure it provides through compaction-based and multi-phase flow modeling. And finally, hydrocarbon charge. This is the word of petroleum system, in which we can simulate the entire process from generation, from the source, expulsion, migration, possible phase changes during the entire process. And this is a matter of million barrels oil equivalent, or million TCF, and the ability to preserve that. From these modeling results, we can apply some sensitivity analysis. And therefore, if we tie to the PRMS definition, be able to provide estimates on low, best, high, using a semi-probabilistic approach. So I spoke about numbers, and what we have done in recently is to look at numbers that do characterize these petroleum system components over a worldwide evaluation of more than 500 basins in every type of environment. And you can readily give a grade to these various components with that type of threshold. For instance, reservoir with a porous thickness, whether they are fractured carbonates, turbidites, shoal face, whatever, you can give a number. Lower grade of less than 1 meter, Grade 2 would be 3 meters, and so on, up to the best reservoir we know, where the porous thickness is about 20 meters. The same for the hydrocarbon charge. We want to know the prolificity and the migration distance. And of course, hydrocarbon charge is as a low grade, where it's either speculative, we don't even know if the source is there, or if there is the distance between the carrier bed and the active source is more than 2,000 meters vertically and more than 100 kilometers laterally, and so on, where we find, I would say, good to best reservoir, where the prolificity over the drainage is about 2 to 5 million barrels oil equivalent. And we have a vertical connection, and the lateral migration distance is less than 50 kilometers. For the seal capillary pressure, this is directly driven by the relationship between hydrocarbon column and capillary pressure. So it goes from less than 10 bars in the worst case to more than 100 bars, where it can retain several hundred meters of hydrocarbon column. For the trap size, it's important to see that we have to give a grade according to the environment, because in the offshore, we all know that we need to have a certain volumes to be have a minimal chance to be attractive. So we define the trap size of about 10 square kilometer multiplied by 50 meters with the lowest grade. And the biggest one, as we know, have more than 50 square kilometer per 100 meter average closure in the maximum grade. So this is kind of lowered in the case of onshore, where we even small traps can have a fair grade and be therefore attractive. So grade is one thing. The other is the chance of success to reach that grade. And that's precisely the way we build our play risk maps, is to define areas where the chance of success to find a high grade or very low, medium, or high, depending on the local context of the basin. So for the workflow itself, I've tried to summarize a multidisciplinary approach in which we want to integrate everything. As we all know, we start with some seismic scale analysis to make the structural interpretation, horizons interpretation, and we do a lot of seismic imaging to characterize what is in between two horizons. The complementary approach is to do some seismic stratigraphy to pinpoint geobodies that could correspond to good reservoir or good seal or good carrier beds. We have to go through a concept in which we construct the gross depositional environment. And at the same time, we work when we have some well data, looking at outcrop, which could constitute analogs, doing fine scale sedimentology and I would say classical petrophysics. The idea there is to integrate all what we learn from there, which sometimes it's semi-quantitative, into modeling. And there are basically two types of process-based modeling. Here is the definition between petroleum system modeling, also called known as basin modeling, and with even importance, sedimentation process modeling, which is called 3D stratigraphic modeling or forward stratigraphic modeling. These models, they are deterministic. They allow for sensitivity analysis, so their output can be directly used to define the prospects, volumes of in place, and ultimately ranking and risking, and provide directly risk play maps of every component and in an integrated way. So let's start with a nice example here of a frontier basin where a model indicated that there was something good to hope for that basin. So let's go back in the 2014 in the Guyana-Suriname basin. At that time, this was a widely underexplored basin. It was known that there was a world-class source rock there, Cenomanian, so Cretaceous of marine, and there was also a canyon, which of course gave good chances to find a good reservoir. But the objective was to explore the deep offshore and trying to detect reservoir traps and knowing that the seal. But the reservoir, we knew that they should be there, but how they were distributed was still a question, and how the hydrocarbon charge was working. The challenges: no well in the deep offshore, and we had to predict the reservoir distribution spatially and stratigraphically. So, 6 years after, there is the situation. 10 discoveries by ExxonMobil, 2 discoveries by Tullow. This is for Guyana, and then going to Suriname. Suriname now is an emerging petroleum country with discoveries as late as 2019. There were new play concepts at the same time, which were suggested by the model, in which some carbonates on top of these clastics and material coming from the canyon. And there was in a shallower play another discovery. So, how to go from frontier to worldwide success? I think Guyana is probably one of the most attractive examples. So, what we did in the initial play work was to gather seismic data. From there, we were able to put my pointer. We were able to reconstruct the positional system, provide gross depths, gross depositional environment maps, and we did some heavy forward stratigraphic modeling. So a first study in 2014 gave us an idea of the total hydrocarbon charge, and we were eventually predicting 12 billion barrels in place as a P50. We did the same type of study for a national oil company, and I had a good idea of the reservoir distribution. And then when things started, we updated some of our maps with the whole basin petroleum system evaluation. Interestingly, after 2017, so up to present day, you can see all the wells that were drilled. When it's green, it means that there was a discovery, oil, and when it's red, it was a dry well or just little show. So we had produced from our play risk maps for reservoir charge and seal, kind of common risk segment, with gray for high risk, medium in yellow, and a low risk or good prospectivity in green, using quantitative thresholds, as well as some confidence. Hatch area are less confident than the full clear area. So 90% of exploration well results were in agreement with our prediction, or better say our prediction were a 90% chance, which is better than the average exploration success rate, by the way. Sorry, it's a little bit too far. So in the petroleum system study, we had predicted that some sort of near stratigraphic trap accumulation, nicely sourced from an efficient drainage area, and all the wells since have been targeting this and have been successful. Going into a bit more detail of what we can do with this type of process modeling, we can typically play different scenarios. If they are equiparable, provide a probability curve, and predict readily net thickness of sands, as well as, last but not least, a Tlc prediction. So we have depositional models that are able to predict the Tlc distribution. Usually, in former studies, we used to have one measurement somewhere, and we just extrapolate the same value everywhere. And we know now that TOC are highly variable depending on the anoxic or preservation conditions of the organic matter. And this model was eventually done 4 years before test well, and which made Popokai, and it was at the same measurements on the TOC, and that the high amplitude that was the target by the well was actually not from a sand sheet, but unfortunately from a slight difference in marl presence. So we predicted that the reservoir could have could be absent according to the model, in contradiction with the seismic. So let's go now to mature basin. So going back to the Asian continent with a quick consideration on West Siberia Basin, which, as you all know, is one of the most prolific petroleum basin on Earth, heavily explored, and we had to evaluate the yet-to-find resources in a small license block within the basin. So first, we evaluated the depositional system, which is characterized in this basin by world-class source rock located at the base of a complex clinoform system where you can recognize shelf-type deposits, then slope-type and bottom slope or tooth-set turbidites, and this is valid all over the basin. So since we had a lot of control on the basin, we were able to build a forward stratigraphic model in which every type of facies was predicted, and from there extracted the facies that were attractive from a reservoir standpoint. That means sandy deep turbidite or slope turbidite, which appear as small sheets belonging to the various clinoforms that we can recognize on this model. At the same time, perform the basin modeling to understand better the system. So since it was in Russia, it is in Russian. And you can recognize that the way these clinoform are charged is both through lateral migration pathways, so carrier beds that can send the hydrocarbons quite far away from the active source, but also vertically. And when the conjunction of lateral and vertical is effective, then we can have the biggest accumulation. At the same time, the system demonstrated that we could charge underlying reservoir in the source rock per the Sansom migration, which physically is totally understandable because hydrocarbon pressure in active generated source is always higher than hydrostatic. And if the reservoir is hydrostatic, then you can push the hydrocarbons to the reservoir. So opening there a play which was less explored. We looking at this particular example, we could simulate this combined vertical and lateral migration between the various reservoir plays in the various accumulation. So this type of modeling had the advantage is that it could calibrate it quantitatively on the proven volumes using a series of cutoff, and could evidence that at least most of the overlying reservoirs in this clinoform complex, most of the discovery had been made, and only 10 or 20% was to be expected. But and explaining exactly how the field spill mechanism was working in that type of basin, using as a reference the facies maps that we had built for each of the play units or clinoform units, combining shale, mixed, poor quality reservoir, and turbidites located in some locations at the base of the slope. The advantage of process-based modeling, for instance, in the forward stratigraphic model, is that not only you predict reservoir presence, but you can also predict its internal structure thanks to its very high resolution. So you can differentiate through the model a case where we have almost pure shale, a case where we have a few thin beds, and you can define their thickness, and comparing a situation in which you have a lot of thin beds and spaced thicker beds, and of course the case where it's only almost a single pack. So then integrating the nets, in case of sands, the net sand thickness and the number of beds which have less than, let's say, 20 meter thick and more than 20 meter thick. The same with the seal. It's obvious that the thin shale layer is less effective than the thick one, and therefore be able to count the effective seal. So combining this, be able to say something about the reservoir quality. Ultimately, as it is done in the classical play risk approach, cumulative common risk segments, you just sum these maps into a CCRS map. The beauty with the modeling is that you can do this almost automatically and provide reliable CCRS in a much faster and more quantified way. So the level of high, medium, or low risk can be translated into beds thicker than such thickness, charge higher than that amount of million barrels, and seal having a higher capillary pressure above a certain threshold. So it's quantified. So, and as a conclusion, and I hope I have not overpassed my time, is that...
Can you wrap up quickly, please?
Yeah, it's a conclusion, yes. The process-based modeling in play-based evaluation provide quantitative estimates on, as we have seen, reservoir net thickness and porous thickness, seal efficiency, oil and gas charge. We can generate play component risk maps can be generated, but to make it work, we always have to calibrate models against observation within an acceptable precision. We have to perform sensitivity analysis. I'm sorry, the time is running out, but the best way to do an effective exploration is always to identify the weakest petroleum system component and put focus to see its real value. I'd like to acknowledge DGS for allowing me to give this presentation, and I thank you very much for your attention. Good.
Okay. Thank you, Dr. Pierre, for this interesting presentation, particularly the Guyana-Suriname discovery and how it came about. We all have read through various sources. So now I move on to the next presentation, which is by Dr. Owen Sutchliffe. Over to Owen. You can start your presentation.
Okay, thank you very much. I should be sharing my screen now. Can anyone see anything at the minute? Hello?
Yeah, it's visible, Dr. Sutchliffe.
It's visible. It's
Oh, it's visible. Okay. Okay. Okay, so while the screen's sort of going to get started, I'll kick off just with a little introduction. So in this presentation today, what we're fundamentally going to talk about is the technologies that can be used to basically transform the entire part of play-based exploration. And what we want to do with this really is make that process from making initial predictions and concepts to actually defining the prospects and evaluating the prospects so much quicker. Now, The nature of the presentation that we'll go through. First of all, I want to talk about how we can, as an organization, start to increase exploration success rates by creating aggregated databases that allow us to have much greater knowledge of plays, not only in your selected study areas, but at the globe, to inform and make better analog selections. We'll then talk about how we can actually change the entirety of the workflow, how we do the workflow itself, and actually create a standardized repository for knowledge, which is in fact something like a subsurface digital twin. And then what I want to talk about on there is how we can actually start to change the assessment of what plays, what basins, etc., to go into, so we can actually fundamentally change the resource trajectories that we have and make the best strategic decisions possible. Now, on this slide here, what I hope you can see is time on the x-axis and the project finances on the y-axis over here. Now, a typical trajectory of these costs. Obviously, costs are increasing as you go through. You find an exploration well, you appraise that well, and ultimately at some point the project comes on production. And hopefully the area under this part of the curve is smaller than the area under that part of the curve, and that's how we generate revenue. Now, in order to optimize the exploration, there are various ways in which we can do this. One of the first ways is actually reduce the cost of the exploration itself. That means using your technology more efficiently, using your human resource more efficiently, etc., so that the area under this part of the curve is smaller than the area under that part of the curve. The next thing that we can do is actually evaluate things more efficiently. So if you can expedite exploration by 1 year, the net present value of that asset actually increases by around about 11%. So that's about doing your work much more efficiently. Now, there's another way. Obviously, as an organization, we can help improve exploration, and that's identify the right plays that are the most cost efficient for us. So this is about the concept that you select to do the exploration. And part of the next bit of the discussion here that we're going to be talking about is around selecting the best play concepts. Now, the basic requirement for play-based exploration, which is a proven method really to enhance your exploration success rates, is essentially to have a holistic view of the basin in its entirety. So you need to have an understanding of what the source rocks, what the reservoirs, and what the seals are, i.e. the petroleum system elements, but also the processes that actually trap and retain the hydrocarbons in the system. So that's the migration, that's how it's trapped, and then how it's preserved. And all of these things need to be modeled. And in many cases, in the areas of frontier exploration, we actually don't generally have the data to make those predictions. So we've actually really got to use physics-based modeling or other processes, as the former presenter demonstrated, to actually make our interpolations of the subsurface. Now, here's just an overview of some of the most prolific petroleum systems on the planet today. And the point that I'm trying to show on this is that petroleum systems are heterogeneous, and we really need to be able to capture our knowledge as we go along, so we understand the processes that lead to the accumulation in different basins, so that we can apply them to our own studies when we're trying to make more informed opinions. Now, what you can see on this, for example, some petroleum systems form an oceanic crust, are associated with major deltas that either have salt or don't have salt, I should say, mobile salt. Other examples, we can see the accumulation of hydrocarbons in lacustrine basins, in sag basins, in foreland basins, in broad empiric platforms with mixed carbonate clastic systems like what you see in the Middle East. The diversity is huge, and we need to be able to capture that knowledge so we have a better understanding of the systems. Now, in the Navtex portfolio itself, there are three main components that we use to help capture that knowledge, and these are our plate tectonic model, These are our paleoclimatic models. And most importantly for us, our sequence stratigraphic model that allows us to be much more predictive about the architectures that we see in the subsurface. And then we use these three components to provide attributes on all the different geological data that we get, so we can standardize interpretations of geology, depositional environment, and also geological time, which allow us to make a set of products that effectively standardize the stratigraphy and allow us to understand the organization of system tracks in time and in space. And it's through this then that we can start to aggregate the data into a variety of play concepts and ultimately evaluate them more efficiently using the kind of play fairway methodologies that have probably been described in other presentations. However, we don't like to stop there really, and we actually create accessible dashboards and databases of these, where we not only collate the main play components, i.e. what the reservoirs, source rock seals are, what the nature of the depositional environments are, for example, but you also look at the qualities of those systems. Now, for something like a petroleum system, there are multiple elements involved, and we need to be able to rank, score, and assess each of the elements, aggregate them at different levels, and aggregate them at the entirety of the system itself, so that we can try to do informative cross plots that help us understand much better the qualities of these systems. Now, I'm going to show you an example here of how we've done this for the Albion time over here. So here we can see an Albion, an Albion palimpsestic view of the world. We can see the sea level eustatic events that occurred throughout the Albion. We see a high in sea level, the Aptian, I beg your pardon. We can see a high in sea level right at the base of the Aptian, a major sea level fall towards the end of the Aptian, and a major flood at the end of it. And these are some of the oceanoxic events. Now, in the paleogeographically, many of the oceans at this time were restricted, which allowed the accumulation of organic rich matter throughout large parts of the world. These restricted environments were then flooded. That allowed the accumulation of organic rich sediments, as I mentioned. There's a major sea level fall. That allowed the accumulation of salts in these basins over here, and as such form the main components, the seals to major petroleum systems. In the Middle East, obviously this is a time of widespread carbonate deposition in this tropical realm. Not only did we see some major reservoirs forming over here, but the reservoir quality was improved through karstification on top of these platforms, and that was at this sea level event over here. Now, the final part of the story occurs in these high latitude positions, where we have siliciclastic deposition, high rates of sea level fall result in incised valleys. A high rate of sea level rise at these events over here actually allows then to create the infill. So what we see here is during a time when we have high variability in the nature of the eustatic change, we actually see a greater intercalation of petroleum system elements and the development of plays across the globe. This is an example of the kind of knowledge that we get from these aggregated data sets. So I'll talk a little bit more now about actual how we do the work itself. Now, in any working process, as far as I appreciate, there are always three main components of that. There's how you acquire knowledge and process data. There's how you then interpret that data and how you integrate models. Now, in a standard geological workflow for exploration, this is time, and it generally takes quite a long time to do it. You know, on average, many companies work on a kind of 2-year cycle for this. And what companies now want to do are foreshorten this so that, in essence, we retain our knowledge quicker, we interpret our data faster, and we integrate our models more regularly so that we can effectively accelerate the decisions. Now, one way we do this is to actually create a subsurface digital twin, which I'll go into in a minute. But we also need to enhance our collaboration that we have between our different divisions, and that allows us to exchange information and data much quicker between ourselves. Now, this slide here, I'm just really trying to point out a number of things that can happen when we poor at collaborating. So in many different databases, and this is just an example from the Volve data set of Norway, we can see a multitude of picks existing in that database that are essentially for the same stratigraphic horizon. We can see faults that are picted that have different sort of dips and azimuths that are essentially the same faults. And you can see these quite nicely picked down here. Now, also, there's the fact that these picks aren't tying to any kind of seismic event. And what this just tells us is that these data types have been worked independently and not in one common framework. And as such, it adds a great deal of uncertainty into the final geological model. So a solution for this really is to work on top of an open collaborative platform that allows all of the different parts of a workflow to component to be shared, so that you can exchange and transfer ideas. And in this way, we can augment and improve collaboration. Now, one of the challenges that we have as an industry is that we are making models multiple times. An explorationist makes one model at one scale. A production geologist makes a model of exactly the same rocks at slightly different scales. And we can't use either of these to tie together. So we need to have this concept of a digital twin where we can keep these different models live and updated and use data where we need it, and have the capacity and propensity to be able to view models at different scales. Now, if we're going to do this, we also need to condition these models by data. And here I can see just a small synopsis, if you like, of an exploration workflow, where we can see the components of data gathering, the construction of tectonic, stratigraphic, and petroleum occurrence models, lead generation and basin models. And all of these are fundamentally driven by data. Now, we are advocates of using cloud computing to actually augment different parts of these workflows, but not just an individual small component, all of the workflows through having cloud-assisted interpretation for both seismic data and the lithology data that we have in the wells. Now, it's also important, if we're really going to transform workflows, that we don't rely on old technology. And some of these old technologies are grid technologies that allows us to create earth models. For us, we try to develop and evolve technologies that are scalable, that don't rely on the grids, and that can allow different geological data to be viewed at different scales without a decay or reduction in the fidelity of the data. And that's scalable earth modeling there. Now, I'm going to really just sort of conclude this presentation with an overview of a different way of looking at the resource trajectories of basins, the creaming curves that many people use. And I'm going to use an example here from the super basins of the world, which was an area of interest to many people. Now, first and foremost, when we look at the reserves, we can see a plot here of the amount of resource versus the area of the basin, and in general, there's kind of a positive correlation, but there's probably about 2 to 3 orders of magnitude in the range of that resource. Now, that tells us that there are different qualities of petroleum systems that generate these factors. Also, when we look at the creaming curves of the super basins, we can actually start to look at two main populations over here. We can see one where we have 5 billion barrels of oil equivalent, but there's been a huge number of exploration wells to find it, versus those petroleum systems that are geologically huge and are probably just the resource that's available in them are a reflection of the exceptional nature of that system. Now, in my haste, I forgot to give you a definition of what super basins are. A tier 1 super basin is a basin that has 5 billion barrels of oil equivalent that have been produced and has that same volume in reserve. And a tier 2 super basin is a basin that has either of those features. Apologies, I should have kicked off by saying that. Now, when we look at the petroleum systems in what are always referred to as world class, these kind of epithets get used to things quite freely but without definition. Here we can see two petroleum systems, one from the Gulf of Mexico, where we have two source rocks stacked on top of one another, and a wide range of different play types that occur in the material above that. And then we can see a sort of play cross section from the Middle East, where we also have two petroleum systems, large structures, and a wide variety of play types in this case. However, these two petroleum systems are very, very different, because when we look at the Gulf of Mexico, and we can see the resource recovered here, it's almost like the oil has been smeared all over the basin, and we have lots of accumulations in much smaller fields, whereas in the Middle East, these are much more focused, much more charged, much more drained, and in larger deposition, in larger structures. So there's a real dichotomy that we have in here. Now, when we're evaluating petroleum systems, we need to sort of remove any geological bias of it. And here we can see a plot of petroleum system age versus the frequency that they occur. Now, here we can take a global view of the petroleum systems, and we can see there's obviously a peak in the Cretaceous. There's a high number of petroleum systems that are Jurassic in age, and an unusual peak here in the Devonian. That peak is represented well for the Tier 1 superbasins and also for the Tier 2. But the Jurassic seems to be underrepresented in this. So is this a fact of the quality of the petroleum systems or the amount of effort? Now, we can use our kind of plots on here to understand this. And when we look at superbasins holistically, we can see that about 30% of them, have actually high quality petroleum systems versus those that are either what I call the processes are more enhanced relative to the elements. And these dominate the qualities of petroleum systems as we would expect. Now, looking in a little more detail at those two distinct time intervals that I was talking about, the Devonian and the late Jurassic, what we can see from the Devonian is a widespread of interest in the Devonian on a continent where the Devonian is preserved, and this is North America. But when we look at the petroleum systems themselves, there's actually a relatively small proportion of these high-quality petroleum systems in comparison to those of the Jurassic, which are kind of exceptional. And so in this way, we were able to discriminate the effort that has gone into producing the resource for a North American market versus the actual quality of the petroleum systems. And we're able to avoid using terms like, the best, the greatest, and as such, help to standardize our evaluations. Now, I think that the final part of this presentation, what we can do here is just look at how we compare the qualities then with the actual potency of the systems. Now, when we're looking at the basins all have different sizes, shapes, volumes, resources, whatever. And what we do when we're analyzing these basins, we normalize the volume of that resource. In this case, to 1 kilometer cube. It could be any volume. It doesn't matter what you normalize to. But in that, then we get a way and a method of comparing what is the productive area of a basin that can deliver that volume, what is the patchiness of the resource, and what are the number of wells that can do it. And as such, we standardize our interpretation of the resource. We can then start to do some quite neat things with it and actually start to look at how much area is left to explore versus how difficult the hydrocarbons are to find. And these are represented by those different sort of quadrants that are represented on this graph here. It just gives us a little bit more information about the petroleum systems. And when we look at the real world data from these super basins, we can actually see there's a wide range of potential that's represented within this. And this really starts to help us much better illuminate where we should be considering for exploration. And there's nothing stopping us doing this for any other countries. However, we don't need to look at the final state of it. We can look at the trajectory of this through time and to see how the resource evolved. And we can see similar components to creaming curves. So this irregular path as we're establishing the plays, then a sort of a more irregular walk to a more steady state walk. And the advantage of doing this in this way, using a normalized curve, we can use the trajectories to help make predictions about the number and the resources that are left to be able to find. It's a neat way, if you like, of reappraising the creaming curve. Now, what I want to show you the examples here, and I think this is my last slide before the conclusions, is some of the insights that we can get out of this. So this is all that population of superbasins populated together, identifying that there is a significant amount of variation in potential over here. But when we look at the geology in detail, or the geological setting in the detail, here we can see sort of some of those broad epiric basins that have a trajectory that's sitting over to the left of this diagram over here that indicates these resources are much easier to find. We can see a component where we see the offshore sort of basins that have a much higher trajectory. These reflect the big finds, the facts that it's harder to find. You're looking at things like stratigraphic traps in offshore basins. So there are many, many subtleties that you can get out of a thorough analysis of these creaming curves that will help you make the best decisions as to which basins you want to take forward. And this, for me, is a new and unique way of doing that. So hopefully, what I've convinced you, there are various ways in which the discovery of hydrocarbons can be optimized. Play-based exploration is a proven method to do this, and it can be assisted through the creation of rigorous creation, if you like, of standardized data, knowledge, and predictions that are the start of the process of creating a digital twin. However, in order to improve and make our hydrocarbons discoveries more efficiently, we need to use our technology better and utilize technology that can allow us to create and aggregate all of our models in one place and view them in the same time. Now, the final part of this is, if we're going to rationalize our portfolio of plays, is absolutely vital that the most prolific plays and basins are considered. And we may need new tools to help us do that in an effective manner. And I thank you very much for your time.
Thank you, Owen. That was an insightful presentation, and really your approach to acquire, integrate, and interpret and integrate the approach and then process of creating a subsurface digital twin was very interesting. Of course, rationalization is essential when you are comparing different geologies across the basins, and that's something you can always optimize when you are dealing with a lot of portfolios. So that was an interesting talk. Now I move on to the last presentation and the third one. Thank you, Owen. And this is by Debjyoti Das. So Debjyoti, can you start your presentation now?
Thank you, sir. Let me share my screen.
Okay.
I'll just give you 1 minute. Is my screen visible? It is in presentation mode, right?
Yes, it is. It is.
Okay. Thank you. So first of all, good morning and good afternoon to all of you who are present in this conference. And I would like to thank DGH management to give me the opportunity to present in this global conference on play-based exploration. So today my topic is play to prospect workflow for drill-ready prospect generation, where mainly I would like to focus on that how we can diminish the roadblock between the scalability between a regional scale model and a prospect scale model, and we can transition from play to prospect along with the knowledge that we gathered at the regional level, and we don't lose the data when we are moving to the prospect scale analysis. So let's start with the basic key exploration challenges that we need to address at different exploration stages, starting from the play level to the prospect level. So at play level, we are mainly focusing on the challenges or the queries that we need to answer. This is related to where to invest time, effort, and cost in terms of exploration, screening the area, bringing investment in the exploration, how the best part of the exploration area can be carved out from the basin or the play to invest our exploration decisions, right? Apart from that, obviously bidding a new license, entering a play, and then the prospect level, how to mature the lead, and also increasing the success rate is one of the major challenges that E&P companies need to focus in the exploration stage. So often we see that in this entire exploration workflow, we move from this regional scale sweet spot identification and screening of the place, identification of the leads, to the prospect generation, drill prospect generation, drilling the prospects. And if we get the discovery, then we move to the reserve part from the resource part by drilling the appraisal wells to understand the commercial viability of the prospects, and based on that, further field development planning and the production stages. So here our journey is from resources to reserve. So we'll see that how from the resources part at the play level, we can assess these things in a more improved and better way, and we can connect it to the prospect level when we are moving towards the reserve estimation. So I would like to start with this basic two case studies that has been done by Shell on the right hand side, you can see, and the other one by Schlumberger with 20 oil companies. So if I see the right one, the case study, you can see here, it is mainly focusing on that they have gathered some data from different wildcat wells, mainly from the frontier areas, where they drilled some random wells without doing the proper assessment of the trap and reservoir and charge and seal. So the four pillars or four components of the exploration model, which need to be addressed in terms of risk associated to the petroleum system elements. So that shows that approximately to get a success of around 4 billion barrel oil equivalent, they had to drill close to 100 wells out of this 165 wells drilled. And then when they are incorporating the results from, for example, from the trap and reservoir understanding by doing some seismic analysis and detail assessment, the efficiency is getting lesser. And if you can see that getting higher, and you can see that the forecasting efficiency is now representing around, to get the similar amount of discovery, they had to drill around 60 wells. And it significantly increased when they actually incorporated all the petroleum system elements in terms of charging, sealing, trap, and reservoir, and they can come up with 20 to 30 wells approximately to address the similar amount of discoveries. So this is just an overall holistic picture that how the exploration integration in terms of different petroleum system elements, starting from the play to prospect level, can help to improve the success rate in different exploration basins. On the left-hand side, if you see the other case study, which is mainly related to the dry hole analysis, where Schlumberger with 20 oil companies tried to gather the information about different dry holes, and they kind of came up with this pie diagram, which is showing approximately 25% of the dry holes were caused because of the reservoir and trap failure. So now you might be surprised that why the trap and reservoir are having less contribution towards the dry hole. The major reason is that even in the play level, when we are actually analyzing the petroleum system modeling and play chance mapping, we are incorporating the petroleum system elements. But due to the scale differentiation, when we are moving from the play to prospect level, somehow we are losing the connection, and we don't take the detailed assessment of the charging and sealing at the prospect level. We generally take the understanding from the basinal geology and the regional understanding, and based on that, we go for the exploration drilling. So that's why most of the cases, it shows that almost 75% of the risk or 75% of the reasons were associated with the charging and sealing part in the exploration drilling. So let's see that how we can incorporate all these different petroleum system elements in terms of risking and come up with a proper resource assessment and prospect assessment workflow. So in my presentation, I have tried to split the presentation in two parts. One is the play level exploration workflow, and the second one is the prospect level. So in the play level exploration workflow, this is a kind of nutshell, which is a very broad overview of the exploration workflow, which starts from the data selection, preparation, building a complete data bank in terms of exploration data, starting from gravity magnetic, seismic, non-seismic, geochemical data, and so on. and then integrating all those data into a GNG assembly model to build the geological model where we can incorporate the different advanced workflows like 4D stratigraphic modeling and the depositional model building, geostatistical modeling based on the data availability to build a geological model. And moving forward, we do the petroleum system modeling, incorporating each and every discipline data to address the challenges related to different petroleum system elements like trap, reservoir, charging, and seal condition. But till now, whatever the model we are building, it is more of like a deterministic approach, apart from some basic uncertainty we done. But we move to the probabilistic approach when we incorporate the risk parameters, that what is the risk of different petroleum system elements, and then finally a probabilistic resource assessment incorporating the risk and the geological understanding together. And another takeaway of this slide that I would like to highlight that this particular exploration workflow is always an iterative process, and it should be a live exploration model rather than multiple different models at different versions. So that the new data, when it will be coming, the model should be editable and auditable enough to keep on getting updated by the new data that is getting acquired at different stages of exploration. And all these processes should be updated accordingly to see that how our exploration understanding at the initial level can be changing, or the play assessment can be differentiating from the previous understanding to the new data assembly. Now, moving forward to the petroleum system modeling part of this entire workflow, mainly I am highlighting this petroleum system modeling part, but obviously there are a lot of GNG work, underlying work should be done in terms of non-seismic, seismic interpretation and geological model building and all these things. So if we see the petroleum system modeling, the unique part of the petroleum system modeling is this is a collaboration model where we are actually collaborating the data from different domains, be it seismic interpretation, the depth maps, the regional gross deposition environment maps. It could be the 4D stratigraphic modeling, the geological process modeling to represent or reproduce the entire process of geological processes within the model. Could be petrophysical analysis in order to define the reservoir. It could be organophases in terms of kinetic of the source rock to understand the source potential, TOC, HI, analog data, and different thermal properties like tectonic history of the basin and the heat flow and all this information. So collaborating all these different multidiscipline data, we come up with a geological model which should run through different type of thermal, compositional, and pressure migration modeling. So if you overall try to divide the entire petroleum system modeling in these three components address different information about different petroleum system elements, which can be further useful to reduce the risk or mitigate the risk associated with that. In the thermal modeling part, we generally address the source maturity, generation potential, exploration timing, which is another risk factor, the timing in terms of charging time and the trap formation time. We also address the pressure and migration model where the reservoir properties like porosity, pore pressure can be predicted. Seal capillary pressure can be predicted, which can be helpful to understand that what is the potential of the seal to withhold the hydrocarbon column height, right? And obviously the composition modeling, which also can be very useful in terms of source rock tracking, which also can help to understand the play definition, that which play is getting charged by which source rock, whether it is a single source rock charging or multiple source rock charging. Similarly, hydrocarbon origin in terms of thermogenic or biogenic, whether we are looking for a biogenic play, thermogenic play, gas-sided play, so different type of unconventional plays as well. And also the quality of hydrocarbon in terms of API, GOR, oil or gas, or maybe the further division of multi-component kinetics to understand the heavy oil, light oil distribution of hydrocarbon within the basin. So this extensive work of petroleum system modeling can provide you a lot of information about the reservoir, source, migration, and all these different petroleum system elements. But till now, what we have seen, it is more of like generating the geological properties, some source rock properties, reservoir properties to understand that what is the potential of different petroleum system elements and what is the potential of petroleum system as a whole. But now, when we are going to the decision-making part, we need to quantify the risk. We need to translate these geological properties into chance of success numbers. So there, in industry, generally two different approaches are taken by different E&P companies when they are doing the play chance mapping to finally identify the assessment units within the play where they will be further applying the resource assessment or to find resource assessment workflow on top of that. So if I see these two different approaches, the first one, the right one, the geological risk assessment is more of a quantitative approach where actually we are trying to quantify the geological risk in such a way so that it can be further utilized for the risk volumetric assessment. On the other hand side, the sweet spot identification, it is more of a relative approach where we do the qualitative approach to understand the good area and moderate area and the bad area. So just addressing some specific chance of success to different geological properties to see that how the transformation function is actually working and the traffic signal mapping can be done on a play-based exploration workflow. So when we are talking about the quantification of the risk on the right-hand side approach that we were talking about, so the first thing that we need to have a standardized risk model, because as we know that based on the approach of the explorationist, whether it is pessimistic approach or optimistic approach, the number of chance of success, the risk may vary a lot because it is a very subjective number. So that's why we need to standardize the risk model. And here two examples I'm giving here, one from the ExxonMobil and one from the Shell model, Shell V exploration model. Both of them are built on similar philosophy, where not only the geological properties are taken into account when we are doing the play chance mapping. The confidence factor is also one of the important components, because a particular model can come up with a very good reservoir porosity prediction or maybe a very good source of maturity prediction. But we don't know that how much data has got into this data, whether it is based on 2D velocity model or it is a 3D velocity model where we have much more information about the depth conversion and all this uncertainty. So that uncertainty part should be incorporated with the risk, and that is done by the confidence factor mapping. So here you can see that low portion is actually negative indication of geology. High is the positive indication of geology that comes from the petroleum system modeling, geological modeling that you have done in the previous steps. But at the same time, some different companies, they use this kind of parameter matrix where based on which we can identify that 3D seismic, 2D seismic density or well density, how we can differentiate the confidence factor from 0 to 1 parameters. And based on that, we can also classify that if it is a very high confidence area with lot of data in terms of seismic and well, obviously the confidence factor should be, the chance of success should be either very high or very low. So just discarding a play or just accepting a play at a very high chance of success, we need to have a very high confidence. As the confidence goes down, the chance of success becomes moderate. And then finally, if you have very low confidence in that case, obviously the chance of success will be close to 0.5. The 0.5 means flipping a coin that we don't know anything about that, which is actually the lowest confidence factor you can see in a exploration work. So this way we can say that this is a two-step approach for the play-based exploration, where the first part is the geological indication through some transformation function, like our respected speakers already presented in their session, that how different parameters we can take, the range we can take to split into low chance of success, moderate chance of success, high chance of success. And so this way you can prepare the transformation function for different parameters like source maturity, reservoir porosity, reservoir presence, adequacy, seal capillary pressure, etc. And then we come up with a perceived COS map, which is actually an intermediate step. That should be collaborated with the confidence map to give it a standardized approach to finally estimate the risk factor of this particular petroleum system element. And that confidence map is linked to this kind of table that different companies have their different templates. And using this V-shell model, you can actually capture the exact chance of success, which will be standardized across the organization, so that from the management perspective, they can compare between the basins, between the plays, and it will be easier for them to do the apple-to-apple comparison. So this way, finally, we can integrate all the chance of success maps for different petroleum system elements. Obviously, the trees can be differing from one particular area to another particular area for different one particular company to different particular company. They have their own risk matrix and risk parameters, that how they are going to define the reservoir risk, how they are going to define the charge risk, whether the timing risk should be taken into account or not. But by the standard process and using that standard risk matrix factor, we can come up with a standard risk maps, which can help you to finally differentiate within the play that which are the assessment units having higher chance of success and which are the assessment units having lower chance of success. So that's why we can call it the CCRS map, which is combined common risk segment map. So now this approach can be in a different way, as I mentioned in the previous slide. That is something related to the relative approach, which is a qualitative approach. So in case of some basins or plays where you have a similar kind of confidence, maybe in the very frontier area where you are planning to do some seismic acquisition, wildcat well drilling, or maybe the block bidding licensing round is going on in these areas, there some companies also take an approach of relative assessment, just assigning some chance of success value based on the geological parameters, and that perceived COS can be considered as the final product for the relative or qualitative approach of the play chance mapping. And this kind of approach also can be quite easily applicable for the unconventional approaches, where we have kind of continuous resource rather than having multiple traps in the basin or play. There we can take this kind of approach, and these play chance maps can be done for shale oil, shale gas separately to have a better strategic point of view from the E&P company side. And finally, I'd like to add one more thing here without going into the detail of the YTF calculation, because already it has been explained by some of the respected presenters and speakers. So here I would just like to mention that this exploration model, as I mentioned earlier as well, it should be an updatable and live exploration model. So here you can see some examples that when we start from a frontier area with very limited data access, with maybe some 2D lines, no wells, and then we start getting the data in terms of 2D seismic density, 3D seismic well information, the play chance map also can be updated, because you will get more confidence, you will get more information, and the result will be updated automatically. So there should be a proper stage-wise exploration model that should be interconnected to each other, and so that the explorationist can see that how the screaming curves or maybe the field size distribution model that they have prepared at the initial stage for the postulated prospects, how it is getting matched with the later stage of the exploration when they have a lot of data with the assessed prospects. So the comparison between the postulated prospect and the assessed prospects are very important when we are doing such stage-wise exploration in a particular basin or in a particular play. And that also helps you to reduce the uncertainty of this field size distribution that you are expecting here. And you can see with time, when you have a lot of assessed prospects, the uncertainty is getting also less, and you also can see whether you are following the trend that you have expected at the initial stage of the exploration. So moving to the last slide of the play-based exploration part, this is just a key mention that I would like to highlight, that this is one of the challenges sometimes we face because of some understanding of that how we can aggregate these assessment units, because we can run the YTF calculation for each assessment unit, and these assessment units should be aggregated to the play level, plays should be aggregated to the basin, and basins to the country level if you are managing a country-based portfolio. So in that case, many times what happens, we add the risk number together to get the risk volume, but in case of success volume, what method we should follow? So generally, it seems like that if you have a success volume for assessment unit 1 and assessment unit 2, so it can be just added up to get the final number for the aggregated volume for these two assessment units. But actually, these success volumes are actually having some probabilistic number assigned to that. So mathematically, we should not add them up. So in order to aggregation part, that where you can get this kind of play-based or basin-based resource assessment, where different plays will be plotted in a probabilistic graph, there we need to aggregate them in a probabilistic approach by finding some aggregated chance of success, and that aggregated chance of success should be incorporated in the calculation to get the probabilistic success case volume for the play or the basin level based on the aggregation of the prospects or assessment units or plays. And there you can see the difference between this summation and the aggregation through a probabilistic approach. So now once we have this aggregation of the basin and play, we understand the play assessment, and we find some kind of assessment units where we should invest money in terms of data acquisition and further effort to find the prospects. Then we come to the prospect assessment workflow. In the prospect assessment workflow, if we see that the workflow is more or less same, except few of the additional things like a detailed geological model building, detailed geostatistical modeling, or maybe some structural faults analysis, advanced geophysics like inversion and AVO analysis. So all these additional things come into the picture when we do the prospect assessment. But overall, if you see, that can be again subdivided into the GNG data assembly, geological interpretation, forward stratigraphic model to build a high resolution model at the reservoir scale, then petroleum system modeling, and further connected to the techno-economics part and the prospect volumetric. So here I would like to highlight the first thing is the petroleum system modeling. Because if you see that generally in our day-to-day exploration workflow, the petroleum system modeling generally is done at the basin level. That's why sometimes we call it basin modeling only. But that is also important to be incorporated in the prospect level. Because when you are running a basin level model, you are missing these data. For example, you are missing the prospect scale interpretation. Some small prospects that cannot be captured at low resolution model, maybe 1 kilometer by 1 kilometer or 500 meter by 500 meter maps at the basin scale. Some stratigraphic attributes like seismic attributes or maybe some advanced forward stratigraphic modeling result for the local phases that also can be missed in a gross deposition environment map. Vertical resolution is compromised due to the simulation capacity or the hardware compatibility. And also some local faults are not generally taken into account in a basin scale model, which is having a huge impact on the local scale migration in terms of faults analysis. So all these results you can incorporate in this local scale high resolution model. And there we come to the transition between a play to prospect workflow. We can run a parent-child connection where it will take the migration from the basin level because the source spot might be residing somewhere outside your study area. And that migration will be redistributed within the prospect level high resolution reservoir model that will tell you that how the migration or the distribution of hydrocarbon is taking place within your block or within your prospect area. That way, you are reducing the risk related to the charge, local charge and sealing, which is one of the major points that I highlighted in the first or second slide, that this is somehow we are missing at the prospect level and it should be integrated together to reduce the risk at the prospect level as well. Just as an example, you can see that this is a regional model which is not showing any hydrocarbon here. But after analyzing the local scale model with a vertical resolution, which is quite high resolution vertical model has been created with some shale information, the local intercalated shales are actually good enough to hold the hydrocarbon at the prospect level. So this way we are moving from the play to prospect level, taking the result from there. Another example, this is from Alaska, where you can see that 4D stratigraphic modeling, forward modeling has been done, where mostly the regressive sands are here, which were looking like a best reservoir, and they drilled few wells and didn't get a success. The major reason, again, the seal quality. The seal is missing here somehow because of a lot of sands and hydrocarbon is not properly arrested. So then this reservoir model and the high resolution forward stratigraphic model actually takes into the picture that there could be a basin floor fan concept. So this is a new play concept, you can say, or the local phases concept, which can be integrated with the play level that comes up from this model. And this model gets integrated with the basinal model, the huge Alaska model at the low resolution. And there from forward modeling, forward stratigraphic modeling to forward petroleum system modeling, we do integrated parent-child migration model, which provides that this particular reservoir actually is having higher potential to get the hydrocarbon because it is enclosed by the shale on top of that. And as per the information that of the biggest stratigraphic play discovery in Alaska, that can be identified by this kind of integrated approach. Then finally, when we did this kind of integrated petroleum system modeling, understanding the risk at the reservoir, the prospect level reservoir, charging, sealing, and migration, then the risk information of the prospect doesn't only depend on the prospect risk. It always should be the product of the play and the prospect risk, because the prospects are being shared in a play, and this is different prospects can belong to the single play, right? So that's why the play chance of success and prospect chance of success would be integrated to get the final risk parameter of the prospect, and that should be integrated with the volume and fluid parameter uncertainty in terms of porosity, saturation, GOR, etc., to get the final probabilistic prospect volumetric along with the risk factors, which is one of the major component in future when you will be doing the ranking of the prospect. Now, moving forward, just some other important factors for the volume dependency and risk dependency in the prospect volumetric. As I mentioned in the previous slide about the probabilistic approach for the volumetric understanding, by taking the uncertainty parameters for different volumetric parameters like porosity, saturation, NTG, etc. Another thing we need to understand that Monte Carlo simulation is just a probabilistic mathematical application. This is just doing the random sampling. It doesn't know about the geology. So let's take an example here. For example, you have a prospect in distal part, you have a prospect in the proximal part. And from a geological point of view, you know that there is a possibility that both the prospects are having reservoir. There is a possibility that none of them having the reservoir because the reservoir didn't came to this from the provenance to this part. Or there could be a possibility that proximal is having reservoir, but the distal part is far away from the provenance, so it is not having the reservoir. But the fourth condition, which Monte Carlo doesn't know, it can create a scenario where distal part is having the reservoir, but the proximal part is not having the reservoir. So this dependency, you can understand that this is geologically may not be correct or very low probability. There you can build this kind of dependency model where you can make these two different prospects dependent, and you can guide the Monte Carlo with geological conditions to improve your probabilistic volumetric as well as your probabilistic risk factor. Apart from that, there are some other scenarios, like there could be a fault between a 4-way, 3-way closer, and based on the fault analysis and the probabilistic approach, you may come up with 3 different scenarios with 3 different probabilistic value. And this is where we need to incorporate all these probabilities, all the geological understanding together. Otherwise, all the detailed GNG understanding that you have built somehow would be lost at the volumetric part, right? So all these scenarios can be probabilistically incorporated when you are making a drilling decision tree for this particular prospect. And finally, this is where generally we always follow, that is the correlation between different parameters. Like porosity saturation is having some parameter correlation in terms of positive correlation in terms of the volume dependency. So these kind of correlation also need to be filled into the Monte Carlo simulation to guide that how the probabilistic simulation should run in an integrated way rather than going in silos for different parameters. So these are the key mentions for the volumetric part. And here we can see that finally in the prospect model, we incorporate the play risk understanding through the segment risk by creating the product and doing the GNG, LGR modeling and parent child modeling. We also see that segment volumetric we can improve by doing the dependency model. And this way we can create a geological prospect model. Now it comes to the value assessment. When we have to do the techno-economics part, we need to incorporate the uncertainty related to production profiles, cash flow models, the cost of well drilling, seismic acquisition, facility designing, as well as the risk related to the scheduling part, hydrocarbon price deck, and etc. So here, the major part is it should be integrated in such a way that we don't need to bring only the P10, P50, P90 numbers from the volumetric to the techno-economics part. It should be the entire P0 to P100 into the techno-economics, where we can collaborate the uncertainty ranges of the volumetric with the uncertainty ranges for production profile and cash flow models. So this way you can also improve your existing production profiles rather than having 3 different production profiles and moving from probabilistic to deterministic. We need to be maintain our probabilistic approach throughout the GNG and the techno-economics part. Then only we can do proper justice to the all GNG work that we have done as an underlying work. That's how
you can wrap up.
Yes, sir. I'll just take 5 minutes maximum. Yeah. So finally, yes, this is just an example that how we are incorporating the scheduling uncertainty and production uncertainty together to finally come up with a exploration decision tree. And this is a probabilistic decision tree where we are incorporating the different uncertainty, different scenarios in terms of 3-way, 4-way closer with rolling up of multiple prospects vertically as well as laterally to get the net present value for different scenarios and finally the expected monetary value for the entire project, which may help us to come up with multiple situations to make the exploration decision. And finally, I'd like to highlight this ranking part. Once we have come up with such decision tree and the techno-economics workflow integrated to the play level, we can build this kind of dashboard, a kind of complete database with a ranking standardization. So similar to the risking standardization, we can do the ranking standardization. It will be a business analytics approach. It will automate the entire ranking process for the decision-making people or the decision makers. And not only for the prospect you can do this, you can similarly replicate this entire dashboard along with the ranking criteria for the play level for different assessment units, as well as for the exploration block level to rank your exploration licensing blocks. So finally, this is my conclusion slide, just to highlight that this is an integrated approach from data management of its basin-wide data, geophysical, geological understanding, petroleum system modeling, to the prospect analysis, while incorporating the information from the regional studies and addressing the challenges to charging and sealing, and finally connecting to a ranking business analytics dashboard to do the portfolio management for the E&P company and for the country portfolio as well. Thank you.
Thank you, Debjyoti. So that was a detailed presentation from play to prospect, and then a lot of new insights have come up. Essentially, as we see, a play-based exploration hinges on petroleum system modeling, identifying petroleum system elements, grading, classifying, and aggregating. And in that process, we have multitudes of multidisciplinary data, which are also of complex nature because of the scale issues, because all these data sources are from different scales. Then in the modeling, we have data-driven approach and a geology-driven approach. And then what we have seen in the presentations that we have process-based modeling approach in which we believe on the geology, but at the same time, it gets validated through the data. It was interesting to see that play-based exploration in the Debjyoti slide has resulted into lesser geological risk, lesser number of dry holes, and then finally we have seen that the success rate is definitely better than in the case of random or what we can also call as serendipity-driven drilling. So that was all interesting from all the speakers. I thank you all the speakers for your nice, detailed, and insightful presentations. We don't have any questions in this session, so then we are naturally close to the session 2, and I will now like to hand over the activities to my host, Chandrima, and then for further announcements. Thank you very much.